All right, today we're going to talk about equilibrium a little bit more in depth. You've heard this word before. If I said just before this chapter, equilibrium, where does your head go? Where should it go? Newton's first. Correct. Sum of forces is equal to 0. Okay? Or if you go to rotation, technically also sum of torques is equal to 0. But to your understanding right now, electrons don't actually have a radius. It's super weird. Okay? So they couldn't actually have a torque even whatsoever. So yeah, sum of forces is equal to 0. Okay? We're going to talk a little bit more in depth, but I'm going to give you about 4 minutes to start a sample problem that you should be able to do. That doesn't mean you will, or if you don't get it, please don't feel like it's the end of the world. But I'm not going to give that much information. Here it is. Imagine there is an electron on the surface of Earth, and there is a second electron above it in equilibrium. How high is the second electron above the first? You'll notice 0 numbers in that problem. Go. I'll draw you a rough picture if it helps. Here's an electron on surface of Earth. The question is, the second electron is how far above it? Now, a couple quick hints. Keep in mind, if I say this, obviously the ground is made out of a lot more positives and negatives. You can go ahead and ignore the charge of everything else. We're just focusing on the charge of them. And 2, keep in mind I said the word electron. The moment I say the word electron or proton, what 2 valuable pieces of information do you have? You have both their charges and their masses, correct. So while I gave you no information by saying electron, I gave you information. Take about 4 minutes to try to do this on your own. If you get entirely stuck and have no idea, where should you begin? Where should you begin? Yeah, force diagram. For the sake of people online, let's set a 4-minute counter so they know. Timer, whatever.
How far? Well, if you force electron has to equal force of gravity, right? The pull has to equal. I'm just saying that, like.
No, we can't use gravity. We're looking at electron versus one electron state. It isn't changing any of your math. Yeah, but these are very more time beyond the gravity between them.
What to do?
You use gravity so you're looking at things like.
Oh, excellent question. When do we use gravity in this chapter? When you're on what scale?
Macro scale.
And what about this problem told you it definitely is the macro scale? Sveinholler told you it's sitting on the surface of Earth, telling you it is not just the electron's gravity we have to consider. If I told you there's 2 electrons in the middle of space, right? But the fact that I told you it's on Earth means all of Earth's mass is pulling on this thing. So is it considerable enough that you probably should pay attention to it? Yes. If you didn't know yet already, there is a gigantic teacher thread going on right now about songs that should be played on the playlist. Hello. Oh, thank you. Oh, hey, could I have, do you have like 1 or 2 more? Okay. Okay, they're all counted.
Force gravity. So, response to force gravity.
Did anybody notice that the answer was just previously on the board? All right.
What have force electron? Times Q squared over R squared. So F.
Aiden, you made me sad by the way. Ain't No Sunshine While She's Gone by Bill Withers is the song they were playing over the top of the speakers. What?
I like that song.
Did you say to me what song are they playing over the top of the speakers when we were in the hallway? You were passing.
No, I said I liked it. I said you were rocking the green. You were rocking the green.
It was Joe, my apologies. I realized it. I apologize. Joe. Ain't No Sunshine While She's Gone by Bill Withers. It's a pretty famous song.
Oh,
I don't feel like Sound of Silence.
I think I have that, guys. Like I think maybe it can be times 1 point. Oh wait, let's do time 80.
You get them the fourth hour, yes.
For the chart, oh, it's squared, so I don't have to worry about that. And then this is divided by. You get 5.07 meters.
Good night. That's aggressive.
No, I got it.
All right.
Quite well.
Time helper done.
Uh,
5.08 meters.
5 point what?
08 meters.
What did I got?
All right. What's the force diagram on the top, guy?
Force gravity and force electric. Force electric is going up, gravity down.
The song. There's no way I can be monetized now. All right. Anyway. Sum of forces. You should still start with Newton's second law, albeit since this is an equilibrium problem. Boom. There it is. Okay. And of course, sum of forces. I don't think I need to do this for you anymore. But here you go. Positive, negative, or force electric is equal to force gravity. What equation should you be using for force gravity? You do not have to do that. Yeah. Okay. Now, you are welcome to use G m1 m2 over r squared, except, yeah, that's going to make your life a lot more difficult. Also, why don't you have to? Why do you know you can use mg? We're on Earth, on the surface of Earth, right? So we can use mg. We can assume that g is 9.8 in that particular case. Now, what equation do we have to use for force electric? Okay, or Coulomb's law. And if you'd like, in this case, you can certainly simplify it to this, although you don't have to. Why can you simplify it to that?
Because you're getting those charges,
They're both electrons. They are the exact same charge, so you're welcome to do that. Kind of keeps things a little bit cleaner when you do that, but of course, you know both, so there it is. So, doing my math here real quick, I'm going to multiply r squared, so it's over on this side, while I divide mg on the other side. And of course, yay, whiteboard, square root both sides, there it is. Plugging my numbers in, here's k. Okay, here's what I prefer to write in, but what is the charge of an electron? 1.6 times 10 to the negative 19th. And remember that if you know that, you are welcome to write out negative e in that particular case. So here we are, negative e squared, divided by, what's the mass of an electron? I usually use 9.1, but 9.11 times 10 to the negative 31st kilograms, and g is 9.8, like it always is. Plug all those numbers in, and if you've done it correctly, you should end up with 5.08 meters. A surprisingly low number, actually, but 5 meters, keep in mind the ceiling is about 3 meters, so the electron would be, of course, 2 meters above that. Why is there such an incredibly large gap there between the two electrons? Well, sure, but I mean, like, why is that so large? Wouldn't you expect them to be closer together? Why is it so much distance? Why is... I was looking for the force electric is vastly stronger, ridiculously stronger than force gravity. That being said, in reality, if an electron was 5 meters away, would you actually be dealing with a single electron pushing on it? Like, are there electrons in this table? Sure. An electron right here, I would not consider a repulsion upwards like I did in the assumption of this particular problem. Why not? No, that's not quite what I'm looking for. There are electrons in this table. Why would I not consider the electrons pushed up? Why didn't we talk about more than one electron?
There's an instant.
Are there negatives in this?
Yeah.
Only?
No.
What charge is this?
It's neutral, so it's not attracting it.
Not quite what I'm looking for, but you are in the right vein. You're right in that area. It's neutral. Why is it neutral? Same number of balance. And therefore, are the electrons that are in that table pushing up on this side right here? Yes, they are. 100% they are. No, they are. They're pushing up very considerably, except what is also in that table? Positives. And what are the equal number of positives if all of the negatives are pushing up considerably? What are the equal number of positives doing? Pulling them down equally. And so what would the net force be on an electron in this spot? 0. So it is not that a neutral doesn't push on a macro scale, because again, atomic scale neutrals don't do anything, okay? A macro scale neutral absolutely does. There is a stupid number of negatives, and my hand is up here right now, right? My hand is has negatives in it, and the negatives in it. Would you expect to push upward because of this table on my negatives? If you hold your hand over a table, do you expect your hand to get shoved up into the air? No. Even though they are pushing up considerably, it's just the positives are pulling down an equal amount. All right. Let's continue this conversation and talk about equilibrium a little bit further. So when you talk in electricity about equilibrium, you don't usually talk about it oftentimes. Students don't often start by talking about it on the macro scale, but we need to kind of combine the two of those together. Meaning, you've already told me, on a macro scale, equilibrium essentially means this. It's Newton's first law, forces are balanced, right? Is Spanauer in equilibrium as he stands here right now? Yep, force gravity down, force normal up. All right, I walk across the room at a constant velocity. Am I in equilibrium? Yes. When am I not in equilibrium? Acceleration. Following Newton's second law. Exactly. Now, so you'll notice in that case, there was either Spanauer was stopped or Spanauer was going at a constant velocity. And within that, there were no, while I was doing that, there was not Newton's second law. Except equilibrium, when we talk about electricity, is a little bit different. Because, let's actually show the demo here. For those of you online, you've definitely seen this before. All right. Charging this up, what charge is on here?
Negative.
Why?
Stronger.
Bunch of electrons. What I want you to imagine right now is the world's craziest mosh party that's happening in here. They're slamming into each other. They do not want to stay here. Why are they staying here? Surrounded on every single side by insulators. By the way, are negatives staying where I'm touching? No, they've definitely jumped into me a long time ago. It's definitely neutral in this area. It's the negatives are all up here. Now I touch this. Yeah, it's been a minute, so air is knocked into it a while now. So it's getting warmer outside, so you can see my demo start to suck a little more. All right, what just happened? Why?
Did you touch it or did you?
You're gonna need more specific.
The electrons went there.
What?
There's like
There was now space to go to.
You're missing a piece.
Electrons push electrons away.
Thank you. You start with that. Electrons are repelling other electrons. There is an inherent force. There is an inherent unbalance of forces. They're not just going to go. The first thing I want you to get away with electricity from is talking about electrons like they're sentient. Where do electrons go? Path of least resistance. Why? Because they choose it. No, absolutely not. They are inanimate objects, not capable of choice. You have to be able to follow the rules on why they get to a particular spot. So, this was negative because it has a bunch of negatives. Mosh pit, they're shoving each other away. Why do they touch? Why do they spread out when they hit here? Because, of course, they're pushing each other, and that's a conductor. If I do the same thing, again, but I touch the table, do you expect the table to now be negative? Maybe a bit in that area, but overall, I would probably say no. What's the difference?
Bigger.
That would imply that this one would be better at taking negative. Why is it not negative and that one is? Yes. This one's a conductor, this one's an insulator, correct. Allows it to flow easily or doesn't flow easily. Okay, so what's going on here right now? What's that? It's not neutral, it has electrons. What are those electrons still doing? Are those electrons stopped on there? No, absolutely not. They are moving around. But would you say this thing is in equilibrium? Yeah, so that's where it gets interesting to talk about equilibrium on an electricity scale. We're going to talk more about equilibrium probably in about a week and a half-ish or so. Okay, but here's what I want to get you started with this. Okay, I'm going to draw electrons as dots just for the sake of simplicity and art right now. Okay, to help you understand this, let's go back and use an analogy that I've used a few times before. We take all of you, we put you in the back of the classroom, or the back room back here. I lock the doors and I ask you to bounce around at random. Okay, obviously don't worry about pain. Okay, that's it's hypothetical. It's not going to be an issue. And then I open the door. What do we expect to happen?
I just got out.
Why?
Because
You're moving around at random. Why are you? Why do we know you're always going to spread out? I mean, I'm with you. I agree that's what's the case. I don't want to take that away from you. But this is what we have to explore. Why? Why does that always happen?
there's now more room for us to jump around it.
Okay. What's that?
If you go towards somewhere that's more full, you'll be bounced away. But when you go towards empty areas,
So you're starting to get an idea. Okay. So what would we say? What's another way to say equilibrium for charges? Like instead of saying equilibrium, so we've already said it today. Okay, the electrons on there are in equilibrium, or they are. That's not quite what I'm looking for.
They bounce out.
Not quite what I'm looking for either. Although I love the try. Keep trying. Don't shy away from it because it's not quite what I'm asking for. But okay, what do we say today? What do electrons do to each other? Repel, such that they spread out. So what was using that? What's another way to say equilibrium?
They're spread out.
They're about evenly spaced out, right? So you'd expect electrons to inherently be spaced out. But here's a question: are they moving? Yes. Are they probably colliding? So when they collide, are they probably following this? No. Well, let's try something else. Let's try something that you guys experience from day to day. Is there a bunch of air molecules in here? Yes. Is it fair to say they're probably in equilibrium? Yes, I would say so. Discuss quickly in your group. How do you know? Like literally sitting here right now, you are taking in scientific information. You are taking an observation of the world around you that lets you know 100% the air molecules in this room are in equilibrium and they are roughly evenly spaced out. Discuss, see if you can't figure that out in about 30 seconds. If you can't, no big, it's not an easy thing to see.
Like I'm gonna get more air along the back. I'm gonna read the front. But maybe not.
Oh yeah.
oh,
What does it go on?
All right, I'm sure many of you have it, but I'm going to try to guide a little bit. Let's do something with that analogy earlier that might help. Okay, and if you have it, if you're pretty sure you have it, kind of keep it to yourself. I want as many people in here to kind of naturally come to it as opposed to just telling you the answer because it's way more satisfying if we can do that. Okay, so let's imagine now we have everybody. Take all those 30 people we were talking about before. Forget the back room. I closed the door. Okay, and I somehow shove you unnaturally into a corner. I say unnaturally because you're bouncing around at random. It's going to be very hard for me to corral and make sure. But we put all 30 of you in the corner, and you're bouncing around at random. So to roughly draw a picture here. Okay, put a bunch of people in a corner, and don't forget they're moving at random. Okay, what do you expect them to do? Probably, what's that? Disperse. Why?
They want to fill in the empty space.
No, careful talking about these things like they're sentient. I mean, I know people are sentient, but we're talking about moving at random. They're moving at random. Are they choosing to move to a particular area? No. So especially to go back to electrons, let's focus on this little guy right here. Okay? Is it possible that that guy is hit that way? Sure. Is it possible he's hit that way? Sure. Is it possible that he's hit up this way?
Sure.
100%. Okay, and is it possible right now that he's hit back that way? So if I draw those arrows, it looks to be as equally likely as he would hit that way as that way. Okay, since it's equally likely, we could kind of sort of almost cancel them out. When you talk about charges, what you do is you start talking about likelihood and percentage chance. And the thing is, there's so many freaking molecules that it usually works out. the highest likelihood is that this molecule is hit in that direction. Now, when we're talking about electrons, there's like literally, if I have a nano charge on here, remind you, there were about 10 billion electrons on that thing. Okay, now it's a very large number. Is that anything compared to the total number of electrons on the object itself? Absolutely not. No, it's stupid small. But there's 10 billion on there. I'm not going to be able to keep track of all of them. So, is there likely an electron that could go this way and dodge all of the other molecules? Is it possible? Yes, it's possible. Is it nearly as likely as objects going this way? No. Or here's another way to say it. Okay, here's another way to say it right here. Look at this little guy in the center. Is it equally likely to hit left, right, up, or down? Since it is equally as likely to be hit up, down, left, or right, we could say it's in equilibrium. Okay? Or, if it helps, evenly spread out. You know what? Actually, let's use words that you used back in biology. This is basically diffusion. Moving from areas of high concentration to low concentration. And it's not a matter of them wanting to go to low concentration. It's simply a matter of it's where they're the most likely to go because, as Trenton said earlier, they're hit in that direction. So let's go back to a question I asked earlier and see where we are at. If air molecules in this room, instead of people, let's say, we're not going to do this because obviously you need to breathe, but let's say I could somehow gather all the air in this room and shove it into that corner, and then I let it go. Now you can't see the air molecules like you can see people, but how would you absolutely know and experience that it is not currently evenly spaced out, but it is definitely currently trying to get spaced out? What's that? Wind. That's what wind is. Wind is air moving from a high concentration to a lower concentration. The fact that there is no wind in here tells you that, yes, the molecules are currently evenly spaced out, and it is in equilibrium. How are we doing? Again, we'll talk more about this conversation later. Let's get into another math problem real quick to finish up today because it goes hand in hand with your homework. Now, on this next problem, just a heads up, I'll set it up first. Be nice to Rihanna today. Let's just go solid pink here. Okay, I'm gonna set it up first here. Let's say that we have a positive 8 microcoulomb charge, and somewhere over here we have a negative. Sorry, let's go positive again. Let's go positive 12 microcoulomb charge. I want to say that these guys are spaced out between the two of them by about 4 meters. The question that I have, kind of looks like he has a mustache. All right, it's not one. So where could I put a -5 microcoulomb charge so that it is in equilibrium? A couple of things to get you started here. Number one, the fact that I set this up the way that I did, is this the macro scale? No. Simply put, what does that mean for your problem solving?
No gravity.
No gravity. Number two, you will note that I said the equilibrium for this charge. So we're going to focus on that charge. Let's switch colors here actually, so we can highlight a little bit better. Okay, that's not that much better. There we go. Okay. We are not asking every charge to be in equilibrium. We're literally just asking for this guy and only for a single moment. Because probably what's going to happen is, what are these two charges going to do to each other? Repel each other. And when they repel each other, obviously this is going to change this entire answer. So we are just looking at it in this moment, right now, where can I put it? Now I'm going to get you started in a way that I can guess that you guys probably know roughly where to put this ahead. Like if you had to guess right now, before I say anything else, where should it roughly go? What's that? So, but you started, I think maybe even without even realizing you're doing it, somewhere in the middle, yes? Okay. Now I don't always want you to do that. Okay? Because so I'm going to do this as though that's not the case, but try to explain why. Meaning, let's try here. So let's say I put this negative right down here. Okay, how could I easily figure out that that's not the case? Force diagrams. Here's a force diagram. Here's a force there it is. There's force electric. Why did I choose those directions? Attraction, right. Simply put. Could this possibly be balanced in the x?
Yeah.
Possibly, sure. Is it anywhere possible to be balanced in the y? No, so obviously anywhere below is out, anywhere above is out in that particular case. I'm going to go to another spot that probably you wouldn't naturally choose, but maybe you should in the future. What about over here?
They both be attracted to him.
Yeah, they both go right. So even though nothing is in the y, absolutely that's a terrible idea. Same thing over on the right side, yes? Okay, so let's put it somewhere in the middle. And if you had to guess, which one is it? I think you already said it, Jackson. Which side is it probably a little closer to? Why would you guess that?
Because the more positive charge will have to be attracted.
So it's going to have naturally a larger force, but we want them to have the same force. So we need the larger, more naturally big force to also have the larger distance, correct? So here's your force diagram. I'll call that guy F8. And then this one F. That's not F12, that's just F12 for the size of the charge. And you'll notice I up here have my given. I have my force diagram. I am missing my find. So here's what I'm going to do for my find. I'm going to establish a variable. I'm going to say that this distance right here is x. Okay? Now technically over here, this would be another variable. So I could make that y, except there's probably a better thing to put there. What is it? Why is that a better thing to put there than a new variable? Yeah, same, different distance has now only got one possible variable on it. So absolutely that's what we want to do. Now when you write the answer to this, do not ever just write x. Don't just write like the answer's, like if I told you this, I said, hey, here's the picture. Where should I put the -5 Coulomb charge so it's in equilibrium? And you just said 7. That's unhelpful. Okay, you need to basically give a little bit more description. Here's what I would do. I would say it's going to be somewhere in the middle of the two. Okay, and then I'm probably going to give the answer of blah x distance from the 8 microcoulomb charge. But let's do the math. I'm not done here, guys. I got like 5 minutes left, and I need to finish this math. Right? I'm out here at 45. Right?
Yeah.
Yeah. So stick with me here. Okay, where are we going next? Yes, on the forces. And since I said equilibrium, what nice simplification should we make ahead of time?
0.
Acceleration is 0. What are the sum of forces?
F12 minus F8.
Yep. Also, quick reminder what we talked about briefly at the end of last week. Don't forget when you use Coulomb's law and you get positive or negative there, that just means attractive or repulsive. So we always ignore that math. The positive and negatives that are up here are 100% from which direction is it going. That's positive x, that's negative x. Okay, and of course, real simple math here we get to, well, that must mean they must be equal because, of course, a little bit duh. Now I'm going to name these. I'm going to call this guy, let's call this Q8. We'll call this guy Q12, and we'll call this guy, just the center of our attention, we'll just call it just Q. If you wanted to say Q5, that'd be completely fine. I like Q because I know it's going to be it's going to be the same for both. All right, how do I calculate each of these forces? Oh, sorry, before I get away from that, I know I've said this like 9,000 times. If you look at these problems, and again, you're completely confused by the math, I'm going to show in just a second. Bulk of the points. Okay, set up this right over here, bulk of the points. Now let's do the math. All right. What's that called?
The force electric.
You can either call it force electric or what's its other name. That's completely fine. What is its other name? Coulomb's law. Yeah. Just so you know both of them. I'm gonna repeat stuff like this, not that you have to memorize, but it makes it easier to communicate in the future. All right. So how do I calculate force 12 here? K times Q times Q12 all over 4 minus x squared equals. What else? What's the right side?
Times Q times Q 8 over x.
X I don't usually write Kc, by the way. Again, it means Coulomb's constant. It's an extra thing to write down. I just like K. Your personal preference is whatever you'd like. Okay, I'm going to start talking to you about some math here that makes this. I'm going to show you a couple tricks here mathematically that make this a lot easier to do. You are welcome to do this kind of in your own way. If you can't follow any of the tricks, great. Well, let's start off with the super easiest one, and that is this. What should we simplify to begin with? Oh, I disagree. That's not what we should do first. I agree that's definitely something we can do, but what's the easiest thing to do first? K's cancel and Q's cancel. Let's talk about y. Why? Hey, let's go back over the picture. Wouldn't changing Q, like if we doubled Q, wouldn't that change the force? Yeah, it would double the force. So why doesn't that matter? Yep, doubles, and same thing with K, right? K affects both sides the exact same. The exact amounts don't concern us, we just need them to be the same, right? If I wanted to know the amount, like if at the end of the problem I said, how much is that force, would you cancel Q in that case? No, you absolutely have to know what it is in order to cancel it out. Let's keep going. All right, next thing I'm going to show you, I'm going to do something. I've already started doing it. A trick. You'll notice I'm doing something I tell you guys not to do all the time and ignoring my units real quick here. So now I had it up there, but I'm going to continue to ignore those units, and you'll see why in a second. So I'm going to plug numbers in. Okay, Q12 is, what did I say? 12 microcoulombs. You do not have to do this. This is probably the one that people would not catch if they were doing this naturally themselves. What is micro actually? And if it's on both sides, then...
Let's cancel it. Yay.
Arguably, sort of, you can even cancel coulombs to a certain degree because the exact whatever it is doesn't really matter. It's a ratio problem. So here's where we're at. We are at 12 over 4 minus x squared, making our life looking a lot more like a math problem right now, over x squared. Now I'm going to show you one more simplification before we finish this, because I see some of you already going to your calculator, but if you take your time and look at tricks, you can make your work a lot less. If I do this, if I square this out, what does this become?
16 minus 3x.
And that is a,
Quadratic.
which means the only way to solve it algebraically is going to be quadratic equation, or completing the square. Yes? Now I can already see on some of your faces we'd prefer not to do that. Okay? One, you should get good at it. If you're ever ignoring stuff because it's a weakness, don't let it be a weakness long. But let's talk a couple things about that. Number one, the quadratic has two answers. Why does that make sense given the problem to start off with? What are the two answers that it's more than likely giving you? Yeah. One of the answers is going to be this x. The other answer is going to be this guy right over here, which totally makes complete sense. But you know what? I want to make my life a little bit easier, so here's what I'm going to do. Square root everything. Now we are at, now don't forget the squareds up top, but that would be square root of 12 over 4 minus x is equal to the square root of 8 all over x. Should I get an answer now? Should I get one answer? Yeah. Let's finally do what Rihanna suggested a while ago. I'm just going to cross multiply it. Here I get the square root of 12x. That side I'm going to just distribute out, so we have 4 times the square root of 8, and then minus the square root of 8 times x. Let's go ahead and get x's together. So square root of 12x plus square root of 8x is equal to 4 square root of 8, and x is equal to, distributing that out, 4 times the square root of 8 all over square root of 12 plus square root of 8. Let's see what we get.
The square root of 12 times square root 8.
No, it's plus square root of 8. And you end up with 1.79, let's go 1.80. So, let's check if that makes sense. Does it make sense that it's this way closer to the from the center?
Yes.
Yes. If you had put the x here, you would say it's somewhere in between the two of them, 1.8 meters from positive 8 microcoulombs. If you, for some reason, put the x over here, great, that's not a problem. You're going to get a different answer. Your answer is going to be somewhere in the middle of them, 2.2 meters from the right side. Of course, that's going to be the exact same answer. All right, see you guys tomorrow.
They have to play body weight. You see that?
No, did it not? Yes, there is. Oh, there it is. There it is. We're good.